let's derive the Maxwell-Boltzmann distribution. All right, the Maxwell-Boltzmann distribution, right? So we know what the partition function is, right? And what we need to do is, this is this degeneracy factor here. We need to figure out a term for that. The number of levels at per unit energy is what we're after here. We're going to have to get to that. And we're going to do that for this, what we call the particle in a box problem. All right. And for the particle in a box, that's in appendix back of the book, we can determine the number of levels with an energy less than this energy epsilon, right? The number of levels this is with an energy less than energy epsilon is related to a bunch of constants, right? Planck constant, the mass of the molecule, the mass of the particle, and the size of the box, a squared. A is the length of the box, right? So let's differentiate this with respect to energy, all right? And what we can define then is this density of states. The density of states is how many states there are per unit energy. That's just exactly what we need to stuff in back here. And for translational energy, which is the one we're looking at, we know that we've got a continuous distribution. So once we have developed this term for translational energy that we put in there, we can replace the summation with an integration. We're going to integrate from all energy 0 to infinity, and then obtain an expression for the translational partition function. This would be for any gas phase molecule, it turns out, right? The partition function, the translational partition function for a monotonic gas, this is the total partition function, because there only is translation in that case. You'll see the partition function is related to the volume, right? The mass and the temperature. Boltzmann constant, Planck's constant, pi, those are all just constants. 2 is obviously a constant, right? The translational partition function is the only one we're going to find out that depends on the volume. It depends on the size of the container, in other words. Oh, yeah, right. We mentioned that for why it's a continuous distribution. And this term over here, right? This h bar squared 2 pi mkbt to the 1/2, that we call that the thermal wavelength. That term, right? If we cube it, it has to have units of inverse volume. If we have the non-cube version, oh, it's in length, right? Look at that length. The thermal wavelength, I mean, 10 to the minus 14 meters. Yeah, this is why it's this is related to why translation has gone continuous on us. This thermal wavelength, the box has to be really small to get quantum behavior, right? Okay, but calling that the thermal wavelength, we get a really simple expression for the translational partition function. Be careful of your units when you SI units for this. This is, remember, when we got small m, that's the mass of a molecule. KB, that's usually with a molecule, right? Whereas m, the molar mass, that goes with R, the gas constant. So this is the mass of an individual molecule, and the SI units of mass, kilograms, right? Kilograms. There we go. In kilograms per molecule is what we're going to put in here to get the right units for the thermal wavelength. Okay, well, now that we have the translational partition function, we can actually derive the Maxwell-Boltzmann speed distribution, that if we know how the energy levels are partitioned with energy, then we can substitute back in for that e to the alpha term and determine then how the number of, we can transform this into the number of molecules between speed v and v plus delta v, how that relates. Oh yes, that's the same distribution that I showed you earlier. The Maxwell-Boltzmann distribution describes the translational energy of a molecule, and we saw how that depends on temperature for one given molecule, right? It gets broader and the maximum moves out in velocity. for a given molecule as you increase the temperature, or if you stay at one temperature and change the mass from very heavy to very light, again, you get broader distributions, and the maximum moves out as you go to lighter molecules. Lighter molecules are faster. They all have the same energy, right, at the same temperature, but the velocity is different because kinetic energy equals 1/2 mv squared. Okay, so let's just remember what we've seen today. We derived the Maxwell-Boltzmann distribution, which describes the population of translational energy states.